Greetings, everyone, and thank you for tuning into this virtual event from wherever across the globe you're currently situated. My name is Mohammed Shamroukh, CIBSE UAE Yen Technical Officer and Events Coordinator, and together with my colleagues Alejandro, Fahim, we at CIBSE UAE welcome you to today's technical webinar. We are glad that you have joined us to learn from Yara Machnouk and Leonardo Poli of Elementa Consulting, who will be sharing their insights shortly on a very relevant yet still locally underrepresented subject, which is embodied carbon of building services equipment within the context of CIBSE TM65. Now, for those of you who don't know or happen to be unfamiliar with CIBSE's roles and responsibilities as a region, our role here is to promote the intellectual welfare of its members, CIBSE members, and to improve the understanding of building services engineering within our society by organizing events and other activities related to the built environment, such as the one we're having today. Today's agenda items will flow as follows: speaker's introduction, speaker's agenda, session housekeeping notes, speaker presentation, and finally we'll close out with a Q&A session and the closing remarks. It gives me great pleasure in introducing our speakers for the day. Our first speaker today is Yara Machnouk. Yara Machnouk is an environmental design engineer working in the sustainability team at Elementa Consulting. While generally exploring all forms of sustainability within building services and design, she has more recently been focusing on whole life carbon assessments and, to be specific, the embodied carbon impact of MEP materials. She will be speaking about the greatest impact of materials in building construction and highlight guidance on early decision making. Yara is joined by Leonardo Poli, who is an embodied carbon specialist also at Elementa Consulting, with a background of
Sorry guys, is it me or I can't hear Shamroukh?
Yeah, we can't hear him either.
Fahim, can you just pick it up from where he stopped and just continue?
Yeah, sure. So our speakers today are Yara Machnouk and Leonardo Poli from Elementa Consulting, and they would be talking about our topic for embodied carbon. Can you go to the next slide, please? Yeah, so the topics are like embodied carbon in building services, why it matters, basic embodied carbon reduction measures in terms of MEP, and then in terms of the context of CIBSE TM65, a summary and an example. Yeah, so please note that the webinar is being recorded at the moment, so all of you who are in attendance will receive a certificate. If you have any questions, you will need to write them in the QA panel at the end of the session. Please make sure your cameras are off and your mics are muted. Okay, with that, I think Yara, you can start.
Thank you very much for the introduction. I'll go ahead and share. Is that good? And everyone can see full screen. Okay, great. So as Fahim just mentioned, we're going to be talking about TM65, which is the embodied carbon of building services equipment. And I'll be presenting alongside my colleague, Leonardo Poli. just a brief introduction of Elementa Consulting. We're a deep green engineering firm. We have global offices worldwide. We tend to look at a range of MEP consulting and sustainability services and kind of go across the board. So before we go into the kind of technical details of what the CIBSE TM65 methodology is, just to make sure everyone's on the same page, I imagine we have a range of people joining from kind of different backgrounds. So we'll go through the definitions of some of the things we're going to be talking about. First and foremost, embodied carbon. When we say embodied carbon, these are the carbon emissions associated with the materials and the construction processes throughout the whole life cycle of an asset. So this could be a building asset, or as we're talking about today, it would be the product itself, the MEP equipment. So when you do an embodied carbon assessment, you can assess this through a life cycle assessment, which quantifies the environmental impacts. And in this case, we're talking about the global warming potential. The different stages of the life cycle are defined by the EN standard into different stages and submodules, typically A, B, C, and D. And so to summarize, if you were going to carry out an embodied carbon assessment, you would add the carbon emissions of the A stages you see on screen, the B stages excluding operational, which is B6 and B7, and the C stages as well, which is end of life. And typically this would form what is called whole life carbon of a building if you were to add the embodied carbon and the operational carbon together. And we've become really familiar with operational carbon just as an industry, but embodied carbon is that gap that's really being pushed for, and if more so in MEP, as this is something that's not accounted for as often. So why is this conversation even happening? We all know that we need to reduce our carbon emissions. This is something, at least within our industry, we recognize, if not worldwide. And this diagram on screen just represents the color scale of annual temperatures from 1850 up until 2018, 2019. And the IPCC report states that if we want to meet our 2-degree reduction target, we need to reduce our carbon emissions by 80% by 2030. So this all feeds into that wider goal. And embodied carbon specifically is becoming more relevant. As I mentioned, operational carbon has been a focus. The grid is decarbonizing, we're installing more efficient MEP equipment. So as we see the pie chart of embodied versus operational carbon in more recent buildings and new builds, we see that the embodied carbon is really taking over this overall percentage, largely due to the operational really being a focus. So we need to bring the embodied carbon up to that same level. And why MEP specifically as well? There's lots of conversations happening around the embodied carbon of structure and facades. You can find EPDs of different architectural elements, windows, just kind of the skin of the building, but not so much about MEP. It's really an area which lacks data sources, so that's why it kind of gets pushed to the bottom. But if you really think about it, it's something that can be really high in the overall embodied carbon impact of a building. So if we want to think of the quantities, MEP is something that's quite hard to grasp because usually it's hidden. So, you know, it's hidden in risers and ceiling voids and so on. But if we really try and grasp what the overall quantity is, a study from the Carbon Leadership Forum estimates that for a commercial building, it can be between 15 to 25 kilograms CO2 per meter squared. So if you think about this for like a 2,000 meter squared building, you could have about 25 tons of MEP equipment. And just to visualize it even further, that would be kind of equivalent to a thin whale, which, as you can imagine, is massive. And the embodied carbon of MEP, another reason why it's really important is that it's usually made of very high impact materials. So as an example, steel is something that we see used really, really often in a lot of MEP equipment for things like ductwork, casing, piping and pumps. Cast iron we also see a lot, and that's used in kind of component housing of equipment. Aluminium in electric motors and heat exchangers, and as we know, aluminium is something that generally has a high embodied carbon impact, and so on. We see copper being used. LED lights have rare earth elements which also have a high embodied carbon impact. So that's why, you know, it's something really important to consider. And the other thing to keep in mind is MEP generally has quite a high replacement rate. So if we think of the building life cycle being over 30, 60 years, generally the structure would not need to be replaced. The skin as well, unless there's very, unless it's a surface that wears very easily, it's likely that that wouldn't need a full replacement. But MEP is something that you can see typically being replaced every 10 to 15 years, just due to it being the end of life of the product. And this graph is just showing kind of across the building life cycle. Operational is something that we see throughout the building's life cycle. Embodied carbon kind of fills in that gap. We have the really high upfront embodied carbon once we construct the building. We have the consistent repair and replacement impacts throughout the life cycle, and this is where MEP becomes really important. And then, of course, the end of life impacts as well. So this is just feeding into the bigger picture. Now I'm going to go through kind of embodied carbon reduction in MEP design, and it's very basic kind of high level things that you can look at, especially during early stages in the design process. So firstly, less is more. This is something that is kind of self-explanatory. I mean, you can understand that if there's less MEP, there's going to be less of an embodied carbon impact, but it really makes sense when you look at designing a building. So that would include thinking of a fabric first approach, implementing more passive design measures, and all of this is technically designing out the MEP because it would reduce the overall weight of the MEP that you need as you're relying on more passive measures rather than mechanical measures. And when you are going to specify MEP, which is inevitable, look at the products that you're specifying, specify equipment which could have a lower weight, and that's just something to look out for. The second thing is thinking circularly. So specify products that can be demounted and can be reused as well. Think about how they're assembled. So are they using dry fixtures, which are things like bolts, rather than adhesives? That just allows them to be disassembled at their end of life. And also working with architects to consider how the MEP has been designed for inspection, maintenance, and replacement. You don't want to have to be tearing out elements of the architecture in order to reach your MEP. So just that early stage design coordination. And thirdly is to mitigate and reduce the refrigerant leakage. So a lot of the MEP products that we specify for cooling have high refrigerants being used. So just to be conscious of what refrigerant is being used in your product, first of all, ensure that they have low leakage rates and ensure that the refrigerant is 100% recovered. And for anyone who's more interested in this topic, we've also recently produced like a refrigerant leakage best practice guide, which looks into more details on how to mitigate the refrigerant leakage, just because it's such a big impact. This is just a visual representation of low embodied carbon materials. The way that the visual has been laid out, as you can see in the top left corner, a lot of these materials highlighted in pink are things that we typically see being used in architectural elements or design and facade. And the ones in blue are the ones that we'll typically see in MEP. And that's because most of these are metals. And you can see that based on world average carbon coefficients, it really stands out that the metals do have the higher impact. And just for your own reference, if anyone, hopefully everyone's downloaded the TM65 from the CIBSE website, but if not, you can always access it from the link on the website. And we've just included a few slides which have kind of flag placeholders where if you're interested in reading a bit more, you can go to those pages. So I'm going to pass along to Leo now, who's going to talk about EPDs and then take us through the TM65 methodology.
Great, thanks a lot, Yara. And yeah, absolutely. So we're going to kick it off with EPDs, which stands for Environmental Product Declaration, which is actually a good source of information to understand whether or not the product we're assessing is actually low in carbon or not. What is an EPD? Just to bring some clarity onto that, it's a standard way to disclose the information, and the impacts about the product are disclosed also in throughout its life cycle, and it's using a consistent methodology, which is compliant with EN 15804 in Europe, which is the standard defining exactly how to structure an EPD. Where do we find EPDs? Well, the best source of information is usually the manufacturer itself, or we can also have a look at some databases like IBU, which is in Germany, or INEOS in Europe, or EcoPassport again in Europe. And again, Eco Platform is another good source of information. The issue with EPDs is the fact that actually is quite hard to make a comparison between the two. So if we go to the next slide, we see that the important thing that we need to consider is, as they say, apple with apple and oranges with oranges. Whilst EPDs, yes, are regulated by the EN standard, even within the same product type and product category, we find discrepancies, which is relating to different understanding or different revisions of what is called a PCR, which is a product categorization rules, which basically guides you throughout the process of developing an EPD. Hence, the need for consistency, hence it's quite hard to compare these two. This is where the CIBSE TM65 methodology comes in. We're exactly trying to bring that into that conversation. So if we move to the next slide, we see that there is a knowledge gap, and the knowledge gap is exactly what we're trying to fill is in MEP. It's quite hard to find EPDs related to MEP systems, and even if there are any, as we said, there is even also the additional hurdle of, can we compare this? Is it actually developed in the same way? And therefore, unfortunately, there is lack of information. If usually it's quite hard to find, but even if you find information, there might be lack of certainty when it comes to comparing things. So the CIBSE TM65 aim and scope is really on embodied carbon at product level of MEP, and it was to, as we mentioned before, to create a methodology which is consistent to assess embodied carbon values when no EPDs are available. The goal is to create data and make research studies possible, and to make that comparison possible. The hope is that TM65 will also help building services and engineer and industry to improve its knowledge and embodied carbon in building services, and then to make better decisions when developing a whole life cycle assessment and when thinking about different options for their buildings. This is by no means a final process, but is working towards getting that consistency while EPDs are being developed. So how did we develop the process? What are the steps? We have three main steps. As you can see here, we have a data collection phase where products information is gathered from the manufacturer using a manufacturer form, which is an Excel file. Then we move on to the calculation stage, where there are two calculation methods depending on the level of information provided by the manufacturer. We have, as you can see, a section A field which allows us to do a basic calculation, or we have a section A plus B field which allows us to carry out mid-level calculations. The difference in terms of data, if we move to the next slide, we can see that it's well, first of all, we can see that both of them are much easier than an EPD. Basic being really quite approachable by even small to medium-sized manufacturers. Manufacturer involvement is quite low for the basic, so as we said, we don't really need to know that much from the manufacturer, and we can actually get in touch with a few. Mid-level calculation is a bit more, but what we can see is that in EPD, both the manufacturer involvement and how detailed the results are much greater. The limitation here is that the ease of execution of an EPD is not really there, and the information that we need from the manufacturer is a lot. And this is, as we mentioned many times, is where the TM65 fills the gap. So there is a section in the TM65 about the difference between an EPD and what a TM65 is. We can see here it's color coded, so you know exactly what the assumptions are and at which stages, the LC stages, which are A, B, and C up front, in use and end of life. They're all detailed in there. As you can see, it's all greened out for an EPD, whilst there's other gaps that are filled with assumptions in this methodology. You can find this at page 13 and Appendix C of the TM65 methodology. The process, well, basically we have, we want to make clearer that asking an EPD, it should be the first step. So always go for that one. Always mention that it's worth investing the time if they're thinking about developing an EPD. If not available, mention also the fact that this is a conservative type of assessment, and therefore, again, we are pushing further for the development of an EPD if the resources are there. So that's the first thing. The second thing is to ask the manufacturer to complete the form. As we mentioned, there's two different types when there is part A only and part A plus part B. And the last step is sending the information to CIBSE, which is really key, and which is why, which is basically what we will use to create the template, and it might take some time. But the usual thing, the useful thing about this is that we get the information from the manufacturer, we can get back to them and bring some value to them, but also we can create a benchmark for the product and also build a database. So if there are no EPDs for the MEP equipment that you're considering, you need to collect data from the manufacturer. It's the manufacturer form is structured in three sections. Section A, which is the basic, will need the manufacturer to fill out the material composition breakdown, which is actually the most important part. Then there's a section B with supplementary information on the energy consumption. And then if the manufacturer is able to provide this info, there's also additional information that will, we'll happily take on board, and CIBSE will happily take on board, which has nothing to do with the calculations itself, but is actually about improving the next iteration of the process. And before we move on, I just want to mention that in the section A, we need to have at least 95% of the material composition breakdown. We assume that if we get at least 95, that remaining 5% will actually be steel. And if we don't have this basic information, unfortunately, the calculation is not possible. So really big focus on this aspect. So if the manufacturer is able to give you the information concerning section A of the manufacturer form, you can then use these details to develop the basic calculation method. It is the easiest one, and it only has 4 steps, as you can see in the slide. You calculate your A1 emissions linked with the material extraction based on the material composition breakdown and multiplied by the material carbon coefficients, which basically defines how intense in terms of global warming potential a given material is. Then you calculate the emission linked with the repair, meaning the components that are replaced throughout the life of the product. Usually, if not given by the manufacturer, it's about 10% of the overall initial impacts. Then you will use the scale-up factors which changes depending on the product complexity, and then finally we multiply by a buffer factor as we want to make this basic calculation conservative. Finally, if applicable for the product, you can add your refrigerant leakage impact, which is happening during the equipment use and decommissioning. So these are the 4 different steps. Fifth step would be basically just finishing the calculations and getting the final results by combining everything. So for a mid-level calculation, as you can see here, is a bit more detail. So we're digging it in a little bit deeper in what the manufacturing processes associated with this product are. What we see is that here we don't have a scale-up factor anymore, but instead this information can be provided by the manufacturer. A1 is exactly the same. A2 is actually distance of transport and is dependent on the product complexity. A3 is the manufacturing, where we multiply the energy required to make the product by the carbon factor of that country. We take this information from the grid intensity of the country we are talking about. So this information needs to be provided by the manufacturer. Then A4, depending on the factory location, there are standard distances within the UK, and which are going to be applied for transportation. And then we use this additional information to develop stage C2, C3, and C4. C2, we assume 100 kilometers by truck, and then we multiply by the carbon factor. C3 is the same energy used in final assembly to disassemble the product, so just one round, and then instead of multiple rounds if at manufacturing if the product is quite complex. And then carbon emissions, C4 is carbon emission associated with the disposal landfill, which is a standard assumptions on how much is sent to disposal and the energy associated with it. These are all dependent on the UK. Step B3 is actually you carry out step 1 and 2 for the component that are replaced, and then you add all up and you multiply by the buffer factor. After this, we have the information on the product itself, and we can move on to the refrigerant leakage calculation again, if applicable, which is the same as the calculation that we carried out at basic level. Now, we can also, in the next slide, we can also show you what the different assumptions are. As we said, they are location specific for the UK, so you need to be mindful of that if used elsewhere, but basically you can find them in page 17 and 20 of the TM65, or also page 46 of the TM65, again, for additional info. Reporting results, you can clearly you can see that you can clearly outline your inputs and outputs. That's quite important. Transparency is always quite critical when reporting for embodied carbon calculations. We encourage people to be consistent and to make it easier to analyze data, again, in case we need to go back, check the assumptions, then use this information to further improve the methodology in later stages. Next slide actually shows the different impact between using a basic calculation and a mid-level calculation. What we can see here is the basic calculation is quite simple in the sense that we don't have that much granularity or transparency on what's going on behind the curtains in terms of the manufacturing side of things. What we wanted to represent here and pinpoint exactly is the material extraction and the material composition, which you can see highlighted in blue. B3 repair is allocated as, if not provided by the manufacturer, as a percentage. And then you can see the rest is a scale-up factor plus buffer factor, which even compared to a mid-level calculation, which is still conservative compared to an EPD, you can see it's higher. So yet again, another incentive to provide more than less. Even just from the list of different LC modules assessed here, you can see we have much more granularity of what goes on behind the curtains. So one way that I like to describe it to the manufacturer is, yes, you can give us only the basic information, but if you want specific information on your manufacturing line and your production energies, whether or not you're being more sustainable, more you use less energy, we need that information. Otherwise, we have no visibility and we can't represent that properly in our final results for TM65. Moving on, you can see here the appendix in which this is taken actually from the TM65. We also used it in the previous slides. I highly recommend going into the appendix and checking it out so that you can see bit by bit what each individual scope that each individual LC module that we calculate represents, how we do it, and then you can also get an understanding of where we fill those gaps with assumptions. So again, taking an inside look and getting an understanding yourself of the methodology behind it is always advisable.
Thank you, Leo. So I'm going to jump back on just to take us all through a CIBSE TM65 worked example. And the purpose of it is just to kind of highlight some tips and things to look out for when you're going to do this, and also to show you that it is something that actually you can produce quite quickly. So although sometimes it seems complicated at a first glance, it actually could be simpler than you initially thought. So we're going to look at a heat pump, for example. This is information that you would get from a manufacturer. Say that you've sent them the manufacturer form and you told them, can you please give us section A. So they've specified it's a heat pump, we have its weight, we have its capacity, they've given us a material breakdown, and so on. So first thing to ask is this all the information that we need? And first thing to spot is that if we compare the they had only given up to 92%. So that's your first thing. As Leo mentioned earlier, it needs to be a minimum of 95% in order to carry out the calculation. And the next thing is, because it's a heat pump, there's refrigerant associated with it. So it's always important to know the type of refrigerant that's used so we can calculate the global warming potential impact of that refrigerant across the life cycle of the product. So now that we have all of that information, we can go ahead and apply that to the basic calculation method. First thing is the step 1, where we look at all of the materials that they've given us and multiply the proportion of that material by the embodied carbon coefficient. So here we looked at steel, aluminium, plastic, stainless steel, copper, and electronic components, and brass. So those are all the ones that were in the initial manufacturer form. And the thing not to forget is that in order to get it up to the 100%, you always need to account for that remaining 5% of materials. And in all cases, whatever the remaining percentage is, you would just assign that to steel. And that would allow you to complete your step 1 of your calculation. For step 2, these are the repair emissions. So this is the standard 10% if this hasn't been specified by the manufacturer as otherwise. So if A1 is, you can see here, 5,319, you would just add 10% of that for your A1 repair emissions. And then following on from that, we need to add a scale-up factor. So in the TM, there's a table 4.3, which highlights different scale-up factors associated to the complexity of the product. So this is related to the rounds of manufacturing it needs, how many parts are in that piece of equipment, and this will range from, because this can be used, you know, to look at something as small as a valve, for example, or it can be used for a heat pump, which is much more complex in comparison. So if we just think about, you know, the composition of a heat pump, which complexity factor we would use, just logically, because of how it's made up, you can see that we've assigned that to category 3, which is a high complexity factor, which is multiplied by 1.6. In comparison, we can see in low complexity, there's pipes and ducts and valves, for example, which are much smaller and less complex pieces of equipment. And then going on from that, to complete your basic calculation, you always need to multiply this by a conservative buffer factor of 1.3. And this is, as Leo was mentioning before, if the manufacturer isn't able to or isn't keen to dedicate the time to give you, you know, information on the manufacturer, the manufacturing process itself, we still do need to account for that, and that it's a conservative assumption. So that 1.3 is aligned with the French default methodology. And that would give you your final embodied carbon. However, it's still excluding the refrigerant leakage. So the refrigerant leakage is a calculation you add on at the end, and that would be the annual leakage impact of that heat pump product, and you would add it, and then that would give you your total result. As you can see, in comparison, refrigerant leakage is a really high embodied carbon impact for an MEP product. So to give everyone a bit of insight on TM65, next steps and where we go from here now that the calculation methodology has been defined. First thing to consider is today a lot of you know, the attendees we're talking about are based in the UAE, which is the TM65 was tailored towards the UK, and that's where the methodology was created. And there are some things that do need to be accounted for and adjusted if you were to apply it to kind of the UAE or Middle East and you wanted to use it really often. So something that we're looking at is we're working on an addendum of the TM65 for specifically Australia. So what it involves is, you know, working with a working group that's essentially in the area that can do research and provide figures that are relevant to the region. And from that, you can develop your own, you know, standard transportation distances, transport carbon factors, electricity or gas carbon factors that are relevant to the region as well. And then other assumptions related to recycling rates and disposal of the products. So it's just something to keep in mind. If it is of interest and if there's enough interest in the region, there is a way to do that, to tailor it completely kind of to yourself so that you're able to use it more frequently. It just needs obviously time and people working together to find those figures. Another thing that will be coming out shortly as well is a TM65 tool. So at the moment, when you download the TM65 package, it comes with the manufacturer form and the reporting form and the actual guidance, but not a calculator tool for you just to put in the numbers and it give you the results. So that is something that is being developed by CIBSE at the moment, and hopefully will be part of the download package as well, and should make the process a bit more streamlined as well. So this is how it would work. Currently, you get the first three, and the idea is that you add the calculator tool to that package. And to further our kind of research and development and what the TM65 actually produces in terms of a database and results, we're taking this further within Integral and Elementa Consulting to look at the embodied carbon of heating design in residential schemes, which is our first one, which is currently in its final rounds of editing, and also kicking off another one looking at the embodied carbon of HVAC systems in offices. So we can look at resi and commercial and try and get, you know, a rounded picture. So for the embodied carbon of heating design in resi schemes, just going to give a bit of a kind of initial results of what we've found before it goes live and before it gets published. So we looked at around 30 different products with 80 different data points, and we analyzed these at a product level and then at a system level as well. And we looked at comparing individual heating systems and communal heating systems. So you can see here, you know, the diagram shows a range of products. We looked at gathering data for heat generation equipment like gas boilers, the heat pumps. We got pipe information as well, heat emitters. We got the information on some radiators, VRF cassettes, and so on. And this was expanded into 4 different sizes. So we got our terraced house initially and then expanded it across 15 unit development, 100 unit development, and then a 2000 unit development, which is 10 blocks of 200 units, just to see what the difference would be across these different typologies. This graph here shows the average across all the different data points that we collected. So we can see that across the range from heat generation, heat emitters to the ancillaries, everything comes to an average of roughly 9 kilograms of CO2 equivalent per kilogram. And that's just a very high level number to just have in the back of your mind. But that's kind of based on our real data source of TM65 results. That's what the results came out to. And just to show then, so those numbers of the products which I just showed were then expanded into the heating system. So you can see here down the side, an air source heat pump example, a VRF example, direct electric. We've looked at ambient loop, both active and passive. And we did an in-depth study to understand what are the quantities used in each of those systems. And then once we gathered our TM65 data points, we extrapolated those and estimated what they would be and compared those impacts against each other. And last but not least, TM65 training. So this is something that we hold online in collaboration with CIBSE. It's actually held by my 2 colleagues, Clara and Louise, that wrote the document itself. And you can see here, one session's already gone. There's still a future one. I think the tickets also might be sold out for the 17th of November, but CIBSE is always open and keen to add more. So if people are interested, you can always register your interest with CIBSE and they can get that sorted for you. Basically, it's just going to take you through the methodology in more detail, doing more worked examples, and just really giving you that time for Q&A and understanding the methodology in more detail. And on that note, thank you everyone for your time and for listening. I hope you found that useful. We're going to give, I think we have roughly 15 minutes or so left, just for some questions. And if you do think of any questions later, just to let you know that our contact details for both myself and Leo are on the slide, so you can always reach out and we'd be happy to address those later. Thank you, everyone.
Thank you, Yara, and Leonardo for this amazing presentation. Embodied carbon is definitely an element of interest here in the Middle East. That I think responds one of your comments earlier. Definitely, there are many question marks out there. People are still getting educated into this, so it's definitely a very interesting subject. There are some questions that we would like you to respond for us. First of all, Obviously, UK is more advanced into this. Middle East, we're still exploring best ways to implement embodied carbon studies and practices. Is there any assessment, let's say financial or investment return assessment between embodied carbon practices, materials that are better for embodied carbon versus alternatives in the market? Like, has there been any comparison done in the UK where you put on one side, for example, you mentioned at the beginning of the session, aluminium has high rates of embodied carbon. Has there been a study that present alternatives to aluminium, alongside the cost and performance of those in the MEP system, so that perhaps that can, show some interest in developers and clients, so they actually push and support the embodied carbon practices? Is there anything in the UK that can be used as a reference in the Middle East?
Yeah, no, that's an excellent question, and usually, as you can imagine, whenever confronting a client, it's a question that sooner or later does come up in relation to the conversation of embodied carbon. So about product for product conversion, I can't think of anything on top of my head that relates to a cheaper version or a greener version of a product and make it and a cheaper version of the product. What I can say though is that, based on the idea that using less is more embodied carbon efficient and should also be more cost efficient, rather than thinking about a product comparison, we can maybe start focusing on a building system type of comparison. And if the conversation is carried on early on enough, there are actually savings to be made whilst retaining functionality, but it's rather than being made at product level, like the conversation that we're having right now, where we compare one MEP versus another MEP, it might actually be about the conversation of, do we have the possibility of reducing the need for an MEP in the first place by improving the facade performance? And yes, there might be a bit more cost involved with developing a facade that has a performance that is slightly higher, but there are both savings from an embodied carbon perspective as well as cost savings in then reducing the MEP and actually minimizing it. So there is that conversation at product level. I would say that the conception that we all have of greener, it means more expensive. It's to some degree true if we want to compare a product and then make it greener, being exactly the same product, like natural materials tend to have a bit higher cost and might have even high manufacturing costs associated to them. But I think that's a conversation that should be left at the very last when doing an LCA. There's always more to be gained, and there's always more value to be gained when we consider things earlier on rather than later on, which is, later on is when we then go into selecting products and we compare different ones. So I hope that addresses the question, and yeah.
Yeah, it does, Leonardo, definitely it does. Thank you for that. Another element is the beginning of the session, there was a lot of emphasis and reference to get manufacturer data. So perhaps this question links a little bit with the first one. Do manufacturers actually cooperate in providing data, or they offer some form of resistance? For example, if, again, let's use the same element, aluminium, or any other element that might be not favoring really embodied carbon targets. Do they actually cooperate when we need to get this data from them, or there is actually a need to enforce manufacturers to actually provide this data by through regulatory framework? And in connection with this, regulatory frameworks maybe can be created by authorities and developers. having an interest on it, because there is an economical benefit in the medium long term. So do manufacturers cooperate, or do you think there is a need for really a regulatory framework to push this in a transparent way, just to say, in a way? What do you think?
I think that's a fair question, and it's a really good question because we've really seen like a clear difference in manufacturer involvement over the past 2 years in this topic specifically. So first of all, something new and something time consuming to a manufacturer is always something that they might try and question, and fair enough, what's the benefit they're going to get from it? And we really found that a bit more when we were doing our first research study that I was talking about in the residential schemes. It was new to people, nothing was enforcing it. There's no, UK policy that they have to be doing it. But something that's more spoken about and more recognized brings people's attention. So more recently, when we're now kicking off our second research study, we've also been collaborating with manufacturers again, and the response has been really different. It's been very positive. People, specifically in the UK, which are a lot of the manufacturers are reaching out to, are very willing to get involved because it's a topic that's being discussed now, and other manufacturers are being transparent about their embodied carbon. So we could say Mitsubishi, for example, have publicly declared, these are our TM65 results for some of our products. And because that's just so transparent and there for people to see, other manufacturers start to get asked the same question. When we're doing early design on projects, or even more towards the specification stage as well, people are going up to manufacturers and they're telling us this. They're asking them, what's your embodied carbon impact? What's your TM65 impact, specifically if it's UK and they're familiar with it? So that kind of gives manufacturers the, I guess, motivation to be involved, and they understand that the first step of actually, if they're worried about their embodied carbon impact, the first way to actually understand how they can reduce it is to know what their impact is in the first place. So I think once manufacturers understand that, they are willing to be on board. Yeah.
Thanks for that, Yara. Another question comes.
Just on that, also just local policies tend to play a big role in this, like the London GLA policies now requires a whole life carbon assessment, and therefore then in firms such as Elementa or any other firm that carries out life cycle assessment will require this embodied carbon information of MEP. So it's just a conversation that keeps happening, but also trickles down from rather an enforcement on disclosing this information, and then it trickles down from local policies or even countrywide policies.
Yeah, that's a fair point. As you can imagine, because this is a webinar for UAE, perhaps we don't have those things in place yet. So trying to understand from you guys who have expertise on this, how to actually achieve and get this done. So that's very informative. So another question is from Jake Timothy. Jake asks, there is a step-by-step guidance in the UK Green Building Council Net Zero framework, which illustrates the need for passive solutions over efficiency. However, this is such a new topic with embodied carbon. Do we need to further illustrate the concepts and methods to impose passive solutions for embodied carbon in a concise document?
Yeah, I can address that. That's a good question, and I think the simple answer is yes. As you rightfully pointed out, I mean, we know that we can't just keep designing buildings in a way that aren't energy efficient and then putting in systems that we think are really efficient. It's not really attacking the problem in the right way. So I think in terms of operational carbon, you're right, it is something that's really been addressed. For embodied carbon, yeah, we can say, logically you're going to have less MEP and that's going to have less of an embodied carbon impact. But to actually, quantify that and do some case studies and properly, set that out, I think, yeah, that is a resource that is maybe missing at the moment.
Thanks for that. I think another element is during the the explanation, it was mentioned that sometimes you might not get all the data from manufacturers, and there are some strategies of placing assumptions in order to calculate embodied carbon. What are the risks of, perhaps this leading to inaccuracies in reporting actual embodied carbon values, considering that it has been also mentioned in the presentation that reporting results is something that we need to be careful on how we actually, deliver that.
So yeah, on this, it really just comes down to what do we expect from an LCA, and also acknowledging the maturity of LCA as a practice. There's no point in saying that we fully understand the results and we fully understand what goes into a model, and then just to tick some boxes. So my point of view, and what I find every time that I approach an LCA, is the fact that yes, there are limitations. Yes, the representation of the model might not be 100% accurate of what's going to be built, and that is obviously an information gap that or a knowledge gap that we're trying to fill. But nonetheless, it doesn't take away from the need to even start addressing these things, because what we're seeing right now is that yes, your model might not be exactly correct of, let's say, a baseline model or a starting point before making the improvements for LCA. But then actually, if we model things in a consistent way, so it comes back to that conversation of consistency within the practice of even assessing MEP products. If we keep that consistency, then at least we have a reduction on which we can rely on. And by that, I mean a delta of reduction, which is due to the process that we have been following and the consistency of the process, actually representative of the reduction in itself, a lot more than the individual points. Let's say point A, where you have a base design, and then point B, where you have an improvement. So that is basically the approach that you tend to take, especially in early designs. As you move on further on in the design, the idea of LCA is not static, is in the sense that it should be kept up to date, and it should keep improving as the stages of the construction progress. So once the product become available, you can either get the conversation going with the manufacturer and ask for an EPD, or you can either use the TM65 methodology, or you can then also go off this and try and see what the material build-up for this product is, and include it in your modeling. But the important thing, I think, is really just about consistency, because we know that we can't get 100% correct, but we know that we can ensure that we're comparing the same with the same, and transparency. Always very important to write down the data points that you're including, the whether or not they're conservative, whether or not there is a buffer factor on this, whether or not you've accounted for everything. Sometimes, you might be using the right data, but you might not be fitting the same scope as required by the assessment, and that is in itself a discrepancy. So there's all of these things that come in. It's not a practice that's by any means perfect and final, but there are some key elements that we need to keep in mind, which are, again, transparency, information management, and consistency.
Thank you very much for that, Leonardo. There's one question here. Let's see if you guys get it right. Is there any high-level rule of thumb to convert basic to mid-level results?
So I think, well, there isn't a specific scale-up factor as there are with some of the other things we've spoken about, purely because it needs more of a database to be put together to understand what is the scale-up between a basic and a high level, because currently, it can differ massively between different products depending on their manufacturing processes. I definitely think it's something that is being explored for the next iteration of the TM65, and just understanding that a bit more. But at the moment, yeah, the difference is just due to the data difference, basically, from what you get from the manufacturer.
Thanks for that. There's another question that just came from Neil Bilton. Would you welcome input for manufacturers in relation to their own embodied carbon studies, data, and actual case studies?
Definitely. I mean, that's the first thing is manufacturers can always complete their own EPDs, which is their own embodied carbon studies, which is something that we do encourage, and we think that's the first step always. So that input from manufacturers is always something we're willing to understand and get from them as the first source. And even data and actual case studies, I mean, there's no reason why just because it comes from a manufacturer that it would be different, as long as it's just clear kind of what methodologies are followed. I think that data can be useful anywhere.
Thank you so much, Yara. I think I'm closing now the Q&A panel, mindful of the time. For the audience, as Yara said earlier, any further question that you may have on the subject, please feel free to address those directly to Yara and Leonardo in the email IDs that are reflected in the screen. So I think thank you very much for your participation in the Q&A panel. Mohammed, over to you. Fahim. Actually, someone is in mute.
Yeah, sorry. So, all right, I think that brings us to the end of the day. I would just like to take the opportunity to thank Yara and Leo for their insightful presentations. It has been an interactive Q&A session as well, so thank you all for your participation. Before we end the event, I would just say that for those of you who are not members of CIBSE, please go to our website, www.cibse.org, and see how you could sign up. If you want to reach us out, for those of you who are staying in UAE, please drop us an email at uae@cibse.org. Follow us at our social media platforms in LinkedIn and Twitter and YouTube, as you can see the links in the screen. As a member of the Young Engineers Network, for all the young engineers and students who are part of the session, please reach us out at yenuae@cibse.org. We have some interesting events in the pipeline, so it would be great to have you all involved in those events as well. And I think that's a wrap. Thank you, Yara. Thank you, Leo. Thank you all for your participation. Goodbye for now.
Thank you.
Thanks, everyone.